Right. So this afternoon, our TA is going to be doing a review for quiz 1. So yeah, and next Monday no class, and Wednesday is going to be, the quiz is going to be in class. Starts at 11:05 and ends at 11:55. So 50 minutes in total, and I think our TA sent an announcement that like you're allowed to bring one piece of paper, both sides, and calculator is okay, but no phone or computers. All right. Okay. So today we are going to be talking about the flow separation and stall, but before that we're going to quickly review what we ended up last lecture in doing the stability analysis, right? Okay, so this is the problem we were working on at the end of the last lecture. So everybody got question 1 and 2. So it seems there is no problem in doing that, right? So question 3 is a little bit of interesting, and I'm going to explain it in a way that may be a little bit different from just plugging in the formula, like where the center of lift is. So thin airfoil theory basically explained that the pressure distribution or the vorticity distribution on the airfoil is actually the summation of 2 effects. The first effect is a pure angle of attack term. So that is basically an airfoil that is exactly symmetric, right? Have no camber at all. Airfoil has no camber, has only a A0 term. So A1, A2, etc. are all 0. On the other hand, an airfoil with a camber but no angle of attack, right, has no A0 term but has A1, A2, etc. So an cambered airfoil at non-zero angle of attack can be thought of as the summation of 2 airfoils. One airfoil only has angle of attack, like a symmetric one, and another airfoil have an camber but at a specific angle of attack so that it has no A0 term. Okay, so it is not correct by saying that an cambered airfoil at 0 degree angle of attack has no A0 term. That's actually not correct. But for every cambered airfoil, there is a specific angle of attack for which there is no suction peak at the leading edge. So basically no A0 term, right? So for any cambered airfoil at any angle of attack, you can thought of as the effect of lift or moment being the summation of really 2 things. One is the cambered airfoil, but no angle of attack change, and the other is angle of attack, right? So here, let's just think about this problem 3 in this sense. Okay, so we first work out what is the lift distribution at CL equal to 0.4, right? So we know that, okay, so at CL equal to 0.4, we have, okay, so at 0 degree of angle of attack, we have CL equal to 0.5 for the front airfoil, CL equal to 0 for the after airfoil, right? So the average CL is going to be 0.25. Okay, let's just take it as an approximation, okay? And then, in order for us to achieve an average CL of 0.4, right, we need the average CL to go 0.15 more. Okay, and as we change the angle of attack, both airfoils increases the CL at the same rate, right? The dCL d alpha is equal to 2 pi, according to thin airfoil theory, for any airfoil. Therefore, in order for the average to increase by 0.15, we have to increase each airfoil by 0.15. As a result, the CL at an average CL average equal to 0.4, this airfoil is going to be at 0.65. So let's just ignore these 2 after digits. I mean, it's just to make the calculation a little bit more complex as you carry on. And the after airfoil is going to be at a CL of 0.15. And when you change the angle of attack so that the CL average is equal to 0.5, right? We know both airfoils has to increase the CL by 0.25. Therefore, the front airfoil is going to be at a CL of 0.75. The after airfoil is going to be at an CL of 0.25. Is that right? Okay. And for both cases, so let's just for case 1, let's figure out where the center of lift is going to be. So for case 1, there is a lift of 0.75 times, well, half of rho u squared times the area of this front airfoil, and there is a lift that's equal to, well, I'm doing this for actually the second case, right? For the purple case. And for the after airfoil, we have 0.25 again times exactly the same thing, half rho u squared times s, and plus we have a moment. We have a moment that actually doesn't change as you change angle of attack, right? So the moment is going to be minus let's just say minus 0.1 times half rho u squared times s times c. All right. Okay. So then let's just because this moment centers on the quarter chord of the front airfoil, let's also figure out what is the moment of the after airfoil. The moment of the after airfoil around this point is going to be another minus, because it's nose down moment, minus the lift 0.25 times half rho u squared s times the distance is 2c. Right? So that's the total moment. So the total moment is equal to this, and if you add it up, so we basically have 0.1, well, it's all minus 0.1 plus 0.25 times 2, so plus 0.5 times exactly the same thing, half rho u squared times s times c. All right? So that's the total moment. Okay? And the total force, the total lift force, of course, is this plus this. That's 1 times half rho u squared times s. Now we have the lift. We have the moment, which is 0.6 times the same thing. Well, the same thing times a chord length. So, well, the same thing is actually the same thing, including half. Sorry. Right. Okay. So we have the lift being this, the moment being this. Now, where is the center of lift? It's 0.6c after the quarter chord, right? After where we computed the moment around. So center of lift is going to be at 0.25 plus 0.6 chord from the front leading edge. All right, good. Okay, and you can do the same thing for an average CL of 0.4. That's going to give you some number. But I want to also tell you a different way of doing this. So instead of going through exactly the calculation again to get the number, why do I have this? Okay, instead of going through exactly the same calculation, which might be time consuming, I'm going to tell you another way to, once you figure out the center of lift for one CL, how do I figure out the center of lift for, especially how do I figure out which direction the center of lift changes at a different CL? Okay, remember what I said in the beginning, the moment and lift for a system, right, for an airfoil or multiple airfoils, is the same as a set of cambered airfoils plus a symmetric airfoil but at an angle of attack. So this is actually what we're going to be using here. So the moment and the lift at a slightly lower CL is going to be exactly the moment and lift for this higher CL minus two symmetric airfoils but at a negative angle of attack. All right? So it is like, instead of doing this whole thing for a different CL average, I'm just going to look at the lift and moment for the purple case, then subtract the lift and moment of two symmetric airfoils, both at minus 0.1 lift coefficient. All right, and I add them together, I should be able to get like what the lift and moment is at this lower CL. Does that make sense? I mean, this is because of the A1. So I'm only changing the A1 term, right, as I change the CL by pitching the system, the whole airplane, at a different angle of attack. And changing A1 term, it's the same as adding two symmetric airfoils. Not changing the angle of attack of this system, but adding two symmetric airfoils at a certain angle of attack. Okay, so in this case, I'm going to be adding two symmetric airfoils, and the symmetric airfoils are going to have center of lift on the quarter chord of this and quarter chord of this, right? And both are at minus 0.1 angle of attack. The result is a lift that's, of course, going downward because I'm subtracting, right? It's a negative CL. It's a downward lift centered at here, centered at a quarter chord behind the trailing edge of the front airfoil. Does that make sense? Right, because I have the same CL here and same CL here, right? And there is exactly one chord length in between them. So if I average these two lift downwards of the same magnitude, I would get a lift downwards over here. So essentially, the lift at CL average equal to 0.4 is the same as a lift at 0.85 chord, right, after the leading edge, which is over here, plus a downward lift but behind the tail of the front wing. Okay, let me add it up. So at CL average equal to 0.4, we have a lift of half rho u square times s, which is basically the lift when I have the average CL equal to 0.5, right? At 0.85 c behind the leading edge of the front wing, then plus a lift of what is it? It's minus 0.1 times half of rho u squared s, right? Oh, actually minus 0.2 because I'm summing them up. Minus 0.2, so its average is minus 0.1. So if I sum up both, it's minus 0.2 at 1.25 c behind the front leading edge. Right. Is that any questions on that? Like, why do I get this? So the second line is basically the effect of two symmetric wings, right, posed at an angle that gives both a minus 0.1 lift coefficient. Okay, so the result of this is going to shift the center of lift in which way? So we have a center of lift originally over here, then we push down, right, at somewhere behind. So that center of lift, yes, is going to shift forward.
Are we
right?
like trying to find the same just where CL equals 0.4? by shifting the CL like minus 0.1, that's when we do this? I'm just asking what problem are.
Oh, what we are trying to solve, right? So we already solved the problem at CL average 0.5, right?
Okay.
So now we are thinking about how to solve the problem at CL 0.4. There are two ways. One way is to exactly go through the same procedure. Okay. The other way, I'm trying to make it. The other way is I'm trying to make it simpler by thinking about. Instead of going through the same calculation, I'm just thinking about what's the difference between these two cases. And the difference between these two cases are basically two symmetric airfoils posed at the same angle of attack that gives both symmetric airfoils a minus 0.1 lift coefficient. That's the difference between these two cases. And the difference between these two cases is this line over here, that minus 0.2 half rho u square s of a lift at this location, right? So basically, as you decrease the lift coefficient by pitching the airplane down, we get an additional downforce somewhere downstream of the original center of lift, right? If, for example, the center of gravity was here at 0.5 lift coefficient, okay, that's a kind of a equilibrium flight. And if you pitch down the airplane to get a reduced lift coefficient, we get a downforce towards the tail, right? That kind of pitch the airplane back up again. So that's stability. All right. Okay. So in this particular case, there is a very good way to think about this. That is, if all the airfoils are symmetric, if all the wings have symmetric airfoils, where is the center of lift? We figured out it's a quarter chord after the trailing edge, right? That's the aerodynamic center of the entire airplane. Okay, so here, this 1.25 feet behind the leading edge of the front wing, right? We computed by averaging the quarter chord of the front wing and the after wing. In a general airplane, you would be doing a weighted average of weighted using the area of the wing. Right here, we are thinking the two areas are the same. But in reality, if you have a canard and you have a main wing, then the front canard is going to have a smaller weight, the main wing is going to have a bigger weight. Or if you have a main wing and a horizontal tail, the main wing is going to have a bigger weight, the horizontal tail is going to have a smaller weight. But if you if you do a weighted average of the aerodynamic centers, you get basically this location, right? That is basically where the increment or decrement of the lift is going to be situated at. And if your center of weight is upstream of that, you're stable. If your center of weight is downstream of that, you're unstable. So this is basically the result of the linear superposition, right, that thin airfoil theory gives you. It essentially comes from the idea that changing angle of attack is equivalent of not changing the angle of attack, but adding symmetric airfoils of the same size as your various aerodynamic surfaces. Okay? All right. So this problem can be solved in two ways. One is basically brute force, so basically repeating this calculation. I think you all know how to do twice. Another way is to think about now the aerodynamic center by using the principle of superposition, thinking about adding symmetric airfoils. Any questions? Yes?
I'm going to ask you, like, the brute force part where you put the moment of point 1 and multiply by that term. Why did you multiply the moment by that and then multiply the coefficient of by that same thing?
This is how moment coefficient is defined.
Oh, okay.
Yeah, moment coefficient is defined, so this minus 0.1, right, the cm, is defined as the moment around the quarter chord divided by half rho u squared, that's what we call the dynamic pressure, then divided by the surface of the wing, and then divided by the chord length. So if you look at the unit of like a moment, this is exactly the kind of unit you need to make it non-dimensional. Yeah. Just like we are defining lift coefficient as, like, if we have 0.75 as lift coefficient, you need to multiply this to get the lift. Yeah. Okay, any other questions? Okay, so today we're going to start looking at something now different. Okay, so yeah, before we go there, let's actually look at a little bit more about the multiple wing scenario. So here, in this case, we have two wings, right? A front wing and a back wing. The aerodynamic center, because of the two wings are different size, the aerodynamic center is probably somewhere close to here. It's going to be a weighted average of the quarter chord location of this and the quarter chord location of this, right? And if the center of lift or center of gravity is forward of that aerodynamic center, we have stability. So this is essentially illustrated over here. So in the green line corresponds to this case, and this is a result of CFD calculation. It's basically a computational fluid dynamics calculation. So as I increase in CL, the horizontal tail case, and again, like I should remove this minus sign. So this is the center of lift shifts towards the tail, and we get stability. Okay, and so usually the way we can also plot the CD versus CL for these multiple airplanes. So remember, we have three airplanes. We have an airplane just with an symmetric wing. That's the blue case. It's almost neutrally stable. We have an airplane with a different airfoil, a cambered airfoil. It's unstable, and then we add a horizontal tail. It's going to be stable again, right? But now let's look at the performance of these three different configurations. So if you look at the CD versus CL, CD is the drag of the whole airplane. CL is the lift of the whole airplane. And it's interesting. If you look at just the symmetric airfoil case, we have a CD that increases a lot more rapidly than the other two airfoils, the other two designs with a cambered airfoil, right? While if you look at the cambered airfoil with a horizontal tail, the cambered airfoil with a horizontal tail has a larger lift coefficient at smaller CL, but the lift coefficient at higher CL is although it's bigger than the unstable configuration with only a wing, is a lot smaller than the symmetric airfoil without the horizontal stabilizer. Okay, so why is that the case? Well, if we look at the lift over drag ratio, you get the same thing. So for the symmetric airfoil, it drops very rapidly at higher CL. And for the unstable airfoil, it's the best, but it's unstable, right? If you add a horizontal tail, we get much better L over D at higher lift coefficients, but the L over D at smaller lift coefficients suffers. So why are these this case? It turns out we already have the tools to understand why the horizontal tail case have a lower L over D than the same design or similar designs without horizontal tail. Anybody suggest why that is the case? Like, why does adding a horizontal tail makes the drag higher or makes the L over D lower? Any guesses? Yeah.
You have like a whole other surface that's adding both pressure drag but also like induced drag.
That's right. You have another surface that actually adds both viscous drag and induced drag. And in our homework, we already looked at the induced drag case, right? We already looked at one example where we know adding a more effective horizontal tail actually increases how much induced drag you have. So we have the same airplane, but by shifting the center of gravity forward, right, the horizontal tail actually had to work harder, and the working harder actually makes more induced drag. So this is actually basically the same set of CFD simulation, but at two different angles of attack. So this is for the wing with the horizontal tail. So especially at smaller angle of attack, if you look at the wake, if you look at the z velocity, remember, like in the very beginning, we thought of approximating the downward velocity region as almost like a cylinder, right? So here, we can already see, like in a real calculation, the downward flow is not exactly on the cylinder because the whole wake actually have flow in it, right? But if you look at the blue contour, it's roughly a cylinder. And you get higher downward velocity here, but you get upward velocity here. That's just because of the wing is rectangular. If you have a more tapered wing, the velocity distribution downward is going to be more even, right? Which means it contains less kinetic energy, which means less induced drag. But if you look at this case, we actually get a little bit of upward velocity because of the horizontal tail having to work so hard. All right, so the downward velocity distribution is not as even, which means more kinetic energy is in the wake per integrated momentum, right? Which means to get in the same lift, you are spending more induced drag. Okay, induced drag is basically you're dumping kinetic energy into the wake because you're pushing air down. So if instead of just pushing air down, you push some air down, some air up, you're spending more energy, right? That's what this is doing. Okay, but what we are not explaining is the case where we have a symmetric airfoil at higher lift coefficient. Why is the drag increasing so fast? So that is basically our first introduction to the concept of boundary layer separation and stall. So it turns out that the cambered airfoil, the reason when you go and see airplanes, you find pretty much all wings of airplanes are non-symmetric, right? The reason is that a cambered airfoil, you can much more easily make it more stall resistant. You get much better stall characteristics with a cambered airfoil than with a symmetric airfoil. Okay, and because most of airplanes are designed to generate lift most of the time upwards instead of both ways, cambering actually makes a whole lot of sense. Okay, so for example, this is a CFD calculation of the symmetric airfoil at a higher angle of attack. I think is at the last point where one of these 2 points where the lift coefficient is either 1.0 or 1.2. So what you are seeing here is an oil flow visualization of the surface. So basically here the streamlines you are seeing is the streamline of air very close to the surface. What you see here is that, okay, so for most of the wing, the flow goes downstream. But there is a portion of the wing over which, if you trace the streamlines, it's actually going backwards. And the color represents how fast the flow is going. So there is two kind of big cells of separated region. So that's kind of a partial stall of the wing, where we have been kind of describing the flow in terms of vortices, right? In this region, the vortices are no longer attached to the surface. They are somewhere above the surface. That's flow separation and generates a lot more drag than otherwise. And now if that separation cell spreads over a bigger portion of the wing, you are not only going to be getting more drag, but also going to lose lift. All right, so that's basically what we are going to be talking about in the next few lectures. Okay, so in order to start explaining the boundary layer and its separation, we have to now introduce another force. So previously, our previous version of the Navier-Stokes equation is the du dt, which is basically acceleration, right, is equal to 1 over rho. So this is analogous to 1 over mass times the minus gradient of pressure. So again, this minus grad P minus pressure gradient is force per volume, and the rho is mass per volume. So this is basically F equal to ma, right? Okay, So today we are going to now augment this equation by adding another force. Okay, that's viscous force. And to make things simpler, we are first going to consider the scenario where there is no pressure gradient. So we are going to basically completely look at scenarios where the pressure gradient doesn't exist, which means the pressure is exactly the same everywhere. Well, some people say, okay, when is the case where there is no pressure gradient? Well, there is no pressure gradient when you have a flat plate, right? When you have a plate, infinitely thin plate, that's exactly flush with the incoming stream of air. Okay, we can actually see that if the viscosity of air is small, which it is, the pressure gradient is almost negligible in this case. So we are going to first look into this case. So we're going to throw this away for a moment, okay? And after we get a little more familiar with viscous force and boundary layer, then we are going to bring back this term, look at the non-flat plates, airfoils, in which both the viscous effect and the pressure gradient actually plays a role. Okay, and actually that is going to be the scenario where the flow is going to separate. Okay, if you have no pressure gradient, only viscous effect, the flow is not going to separate. If you only have pressure gradient and no viscous effect, the flow is not going to separate. Once you have both, then you have the possibility. Okay, so first of all, let's actually look at the force that affects the boundary layer. That's what is viscous force. If you actually look at like the NASA's website on Navier-Stokes equation, the viscous term is extraordinarily complicated. So you have the you have the gradient of velocity, which is a 3x3 matrix, right? Because you have three velocities, you have three derivatives. So the x derivative of x velocity, the x derivative of y velocity, the y derivative of x velocity, so you get a 3x3 matrix, and you have to transpose the matrix, add it with the non-transposed matrix, and things like that. So it's actually, to calculate it in the most general case, this is actually pretty complicated. But for most of the scenarios, okay, so it turns out if you just look at the equation, the equations of a stress for a fluid dynamics is more complicated than structural dynamics. But in most the practical scenarios we have to deal with, it's almost exactly the opposite. So the structural equations look simpler, but you have to actually deal with it in pretty complex scenarios. Because like you have like shear, torsion, and all kinds of things. But for fluid dynamics, although the equations look simple, but we usually don't have to deal with scenarios where all the terms are important. So today we are only going to introduce you to this to the viscous force in a very simple scenario. That is when all the flow are basically going in one direction, except for they are going in one direction but at different speeds. Okay, so viscous force actually for fluid dynamics is actually a lot easier to understand than what it looks like if you just stare at the equations. Okay, so here the viscous force. So let's actually first figure out how big it is. Viscous force is proportional to the derivative of velocity. So here, let me just write it out, du x dy. Well, in reality, I should be using partial derivatives because the ux depends on x, y, z, etc. Right? But like just to make it simple, to don't scare us, let's just say it's du x dy. All right, which means, okay, so if we are looking at far away from this boundary layer in the flat plate, right, the free stream is uniform, and in regions where the free stream is not affected by this flat plate, the velocity is uniform and du x dy is equal to 0. That's where the viscous forces are 0. But near the boundary, okay, the flow actually at the boundary, just because like in a real air, it's consisted of molecules, right? And the molecules go in random directions as long as temperature is not zero, right? And some of these molecules are going to bump into the molecules on the surface, and they bounce back at an angle that determined because the surface is not moving and the air is moving. So if a molecule is moving forward, it collides with the molecules on the surface. It bounces back in a random direction that is no longer on average going forward, right? So basically, the average velocity very close to the surface is going to be zero. So that's why the velocity at the surface is going to be zero, right? Okay, so all viscous forces have origin in basically the random motion of molecules. And then, if the rate at which the velocity becomes higher as you move away from the surface is high, then there is a lot of viscous forces. Okay, so it's the same as as if you have friction between solids, but instead of depending on the relative velocity, it depends on the relative velocity per distance. Okay. And so this is an important effect, and then the viscosity is proportional to that. But like exactly how big is that? You have to multiply this velocity gradient by a few things. The first thing you have to multiply is by the viscosity. So this is the viscosity of air. Okay. The second thing you have to multiply is over how big of a surface area you are acting. So this surface area, and in this case, for example, if we are looking at let's just draw a box of fluid. This box is, let's say this is over delta x, this is over delta y, and the depth delta z. All right, then the area is going to be delta x times delta z. So there is viscous force acting. Let me just draw. There is viscous force acting on this direction, on this face and on this face. Okay, but there is going to be no viscous force acting on this face and this face. Okay, it's just because on this face and this face, as you cross this face, the velocity doesn't change, right? If you cross the two side forces, the velocity doesn't change much. But if you cross the green faces, the velocity changes a lot. So viscous forces works on faces that as you move in the normal direction of the face, the velocity changes a lot. Then there is viscous force acting on that face. Okay, so that's what faces viscous force works on. And another thing is, what direction does the viscous force work on? Okay, so here it's very easy to understand is that viscous force always work on the direction that makes the flow move less relative to each other. What does that mean? If you look at the lower face, okay, does the flow move faster or slower above that green lower face?
Faster?
Yes, above the face it moves faster. Therefore, the viscous force tries to slow down the faster fluid above it, right? And of course, we know a force always have exactly the opposite force, counter force, right? Reaction force. So the reaction force of the force that tries to slow down the fluid above tries to accelerate the flow below. So that's what I mean by it always tries to make the velocity of the fluid more equal to each other. Right? That's basically viscous force. Okay? To summarize, on what face does it work on? It works on faces over which if you move across the face, the velocity is different. Okay? And the magnitude is proportional to the rate at which it is different, times the viscosity, which is constant, times the area of that face. Okay, and the direction of the force is basically opposite to the direction of the relative motion, trying to make velocity more equal. All right, yes, question?
So is the viscous force also proportional to the change in velocity in the z direction?
Oh, yes, yes. So if there is a change in velocity in the z direction, yes, there is going to be also a viscous force working on the xy plane in the constant z plane. Right, so as I said, the viscous force works in the direction over which, as you cross the surface, right, the velocity changes. So if the velocity is not uniform in the z direction, then there is additional viscous force working on this kind of a plane that is proportional to dx times dy, right? But here, this is an analysis in which we assume the velocity is uniform in the z direction, so there is no viscous force acting on the z planes. Yeah. All right. Good question. Any other questions? So this kind of a flow in which the velocity is flows only in one direction, okay, and it only changes, the magnitude only changes as you vary in one other direction. It's called a parallel shear flow. And our boundary layers usually are very approximately, as you zoom in enough, is a parallel shear flow. So this is a parallel, I think it's parallel shear flow. Okay, so now we know the viscous force, right? So let's actually see let's look at what is the effect of the viscous force on this blob of air. Okay, this blob of air, actually, the only force acting on this blob of air is actually viscous force, right? Because there is no pressure gradient anywhere. Okay, and it receives two viscous force, one from below, one from above, right? And we have already said that the viscous force below actually tries to slow it down, because across that face, the air further lower is actually slower than the air within that box. Okay, the viscous force on the green face above, in what direction does it act? Okay, in order to figure out what is the viscous force on the green face above, we have to look at what is the velocity difference above that above green face and below this above green face, right? So if you look at this velocity profile, the velocity keeps increasing as I increasing y. So the velocity above this blob is even faster than the velocity within the blob. And the viscous force always want to make the velocity more equal. So the viscous force on the upper plane tries to accelerate, right, this blob of fluid. Is it clear? I mean, the force working on, yes?
So to make it equal, it works within the control volume, like you said, right? Like it will make that part faster. But you said it also, there's a reactionary force where it wants to make the other parts slower.
Yeah, so maybe I should draw multiple blobs, right? So let's draw a purple blob here, a green blob here, and a black blob here. Okay, so on the purple blob, there is a force from the green blob that tries to slow it down, for which the reactionary force tries to accelerate the green blob, right? Okay, and also on the upper surface, there is the viscous force tries to accelerate the purple blob, and the reactionary force slows down the black blob. All right, and this goes on this goes on like maybe forever, right? Because above the black blob, there may be another blob of fluid, and that blob of fluid, if it is even faster than the black blob, is trying to accelerate the black blob, etc.
So we can view it sort of as like a going like that.
Exactly. That's why we call it like a parallel shear flow, right? It's basically, yes, the force, the viscous force tries to do this to the purple blob. Yeah.
But when measuring the actual viscous force, do we focus on a certain one of those reactionary forces?
Yeah, when we are usually considering like a control volume analysis, right? We're usually considering one blob, and within that one blob, you're going to be considering only the purple force, right? Then, unless you are considering multiple ones at the same time, then you also have to consider the black one.
So for your original example, where we have the one block on the left, we would just be considering, one force basically going to the left. On the bottom, one force going to the right.
Exactly. That's what we are getting to, right? So we on this blob, we have one force from below trying to slow it down. We have another force above trying to accelerate it. So what is the total force? Which one wins? Okay, so you said this one wins. Why is the accelerating force bigger than the decelerating force?
Because the velocity there is higher.
Because the velocity there is higher.
The gradient should be.
Yes, because the velocity gradient below is higher. So if you compare the force above and force below, they have the same viscosity, right? Because both are air. Okay, they have the same area because both are delta x by delta z. The only difference is the dux dy is different. Now, if you look at this velocity profile, how can you tell that the velocity gradient is higher below than above?
Above it's kind of close to zero.
Exactly. Above is closer to zero gradient. So zero gradient would be like a completely vertical slope, right? So, and a large gradient is a very slanted slope. Okay, so above there, the slope is more vertical, which means the gradient is smaller. You know, this gradient is different. This plot is different from usual function plot you see, right? In the usual function plot, the x-axis is horizontal, like f of x is vertical. But in this plot, because we are plotting it in the physical domain, the y-coordinate points upward, and we are taking derivative to y, right? And the u is pointing towards the x direction. So the more vertical it is, the smaller the gradient is, as opposed to like a usual function plot where you see vertical means almost infinite gradient. Here, vertical means zero gradient. Is that clear? Yeah?
What if u0 was very fast compared to everything else? Like, what if this was, like, how would the velocity profile of this change? It would be like less air is, there's a smaller boundary limit, right? If you were to go very, very, very fast.
You mean like if u0 is very fast?
Yeah, if you know u0 is very fast.
Actually, the magnitude of u0 doesn't really matter. What it matters is the relative shape of this. Like, what matters is the shape is the velocity in the boundary layer relative to u0, right? And we're going to see in the case where we have pressure gradient, there are actually cases where the velocity gradient deep within the boundary layer is actually less than the velocity gradient, like closer to the outside. And that's going to be a scenario where the combined viscous forces actually, the viscous force above actually wins, right? So it's kind of accelerates the flow in the boundary layer. But like in a scenario here I'm drawing, any blob you draw is going to have the lower surface winning the tug of war in viscous forces, right? So having the lower surface winning means the combined force goes backward. And if a combined force goes backward, it is accelerating. Is the combined force accelerating or decelerating the fluid? Decelerating the fluid, right? Okay, so that's analysis we are going to be start doing next lecture. That is, how much does the combined viscous force decelerate the fluid? Because that is going to help us understand how fast does the boundary layer propagate. Because if you compare a thin boundary layer here versus a thick boundary layer here, so let's assume the profile is exactly the same, means the downstream boundary layer is just a scaled up version of this thinner boundary layer. Then if you trace the same streamline, you're going to see the same streamline actually is faster here than here, right? Basically, the same streamline actually started somewhere closer to free stream and ended up somewhere closer to the wall, right, relatively. So this is actually a slowed down process. The growth in thickness of the boundary layer is a slowing down process for individual fluid particles within the boundary layer. And exactly how much it slows down is going to tell us exactly how much the boundary layer grows in thickness. And that's going to tell us exactly how thick the boundary layer typically is. All right, so we'll continue that. Actually, Professor Drayler is going to continue that after the quiz next week, so on Friday. All right.
Chi-Chi, do you know who's likely going to be teaching 1613?
1613 is the viscous flow class? It's almost always taught by Professor Drayler. I mean,
He's saying he's not going to teach it.
which semester? Like last time he took a sabbatical, I taught it, but like next semester, I don't think I'm gonna be teaching it.
Sure.
So I don't know.
Okay. Interesting. Because I was talking, he's my advisor, and I was talking with him. I was like, "Are you teaching that next semester?" And he's like, "No, I'm teaching 821. I won't have time."
Oh yeah.
So I don't know. Would it be Dharmafall then?
So is that gonna be? That's usually offered like is it offered every year or is only offered every 2 years?
Every 2 years. And it was not offered last year. So
Oh.
this is yeah.
Okay. Okay, I don't know. Sorry.
No, it's cool. Yeah. I was curious.